Okay, so this video we're going to work through some examples of sketching logarithmic graphs and looking at x and y axis intercepts and also the domain and range of those functions. So my first question that I'm going to work through is sketch the graph of y equals 2 log to the base 10 of 3x and state the domain and range. So to do this, the first thing I'll do is I'll recognize that this 2 in front is a dilation from the x-axis. And it's a dilation by a factor of 2. And 3, this is a dilation from the y-axis, and it's a dilation of a factor of 1/3. Okay, so if I want to draw my graph, I can actually start by drawing the basic function of a log graph. And my basic log graph starts with an asymptote at x equals 0, and it looks like this, and it's got an intercept at the point where x is 1 and y is 0. So this is my standard log graph. Now if I'm going to dilate this by a factor of 2 from the x-axis, what that means is that every value is going to end up twice as far from the x-axis. So this value here will be twice as big, which will end up there. The one on the x-axis stays on the x-axis, and the values on the y values, they all get doubled. So that point's going to end up down there, and my new graph gets stretched. So this would be 2 log 10 of 3x. Now we don't have to worry too much about the base being 10 when we're drawing sketch graphs. That will actually change how quickly the graph grows, but when we're drawing sketch graphs we essentially just recognise that it's a log graph and go from there. So that's the dilation from the x-axis. Now I need to dilate it from the y-axis, and what that's going to look like if we are by a factor of 1/3. So every y value is 1/3 of what it was before. So initially the intercept was at 1. That intercept will now be 1/3 of that distance, which is equal to 1/3. So I end up with an x-axis intercept at 1/3, 0. And all of these points here become 1/3 of the distance that they were before. So in this one here, I've got to move it back. So I sort of break it up into thirds. So that stretches my graph the same as it was before, but it's even sort of like more stretched now. Okay, so this is what my new graph's going to look like, and I typically draw some quick sketches to sort of see what's going on, and then I'll do a good copy of my graph. I can see that the dilations don't affect the asymptote at x equals 0, so that doesn't need to change. But I will redraw the graph and get my new function, and I'm just going to tidy this up a little bit. And I don't need to worry too much about all of the finer details, but I do want to put on an asymptote, and I must write the equation of that asymptote. And we're going to have a sort of skinny, stretched logarithmic graph with an x-axis intercept at 1/3, 0. And there's my entire graph. I can stop there for the graphing part, but I do need to state the domain and range. So the domain of this graph is all of the values that x can be. Now I can see that my x values go from the asymptote at x equals 0 all the way up into infinity. and it doesn't equal the asymptote, so I need a curved bracket, and infinity always has a curved bracket. I could also write this using set notation. This is exactly the same as saying I have the set R, all positive values. And my range of this graph is all of the values that y can be, and because it goes down to negative infinity and up to positive infinity, I can write it as negative infinity to positive infinity, negative infinity to positive infinity, or I can use set notation and just say that it's R. And there's my graph. My x-axis intercept, I can prove that it is at 1/3 if you wanted by solving the equation above. And that looks like this. So the x-intercept is when y equals 0. So if I substitute that into my equation and do the algebra, I get 0 equals 2 log to the base 10 of 3x. Divide both sides by 2 and you get 0 equals log to the base 10 of 3x. Use the inverse of a log, which is an exponent, and I'm going to raise both sides to the base 10. On the left hand side, 10 to the power of 0 is 1, and on the right hand side, the 10 to the power of log 10, they cancel out because they're inverse operations. And then finally, I divide by 3, which is 1/3, and we've also proved that x-axis intercept. Okay, second example. The second example that I want to look at now is when I find the rule for the inverse. And we're going to find the rule for the inverse of 4 times 3 to the power of x plus 2. Okay, so right up at the beginning of the notes for this lesson, we actually had in here, and we've discussed in class, that logarithms and exponents are inverse functions. And what that means is when I graph them and reflect them across the line y equals x, then I can swap the x and the y values around. So when I want to find the inverse, the easiest way to do this is to simply swap the x and the y values around. So if this equation equals y, I'm going to rewrite it as 4 times 3 to the power of y plus 2 equals x. And to get that to its new form, to the inverse form, I'm going to rearrange this equation now to get y back by itself. So my first step to do that is I'm going to do the opposite of plus 2, which is minus 2. I'm going to do the opposite of times 4, which is divide by 4. And then I'm going to do the opposite of a base of 3, and I'm actually going to raise both sides to the power of a log 3. So log 3, 1/4 x minus 2. On the left hand side, the log 3 and the 3 cancel each other out, and I'm just left with y equals log to the base 3 of 1/4 x minus 2. And this is my inverse function. Now for inverse functions, the one extra step that I need is I write it, instead of f of x, I have f to the minus 1 of x. So this is my notation for the inverse function. Alright, so there's my inverse functions. I swap the x and y values around, and then I rearrange the equation to get y back by itself. If you're asked for the domain and range as well, then you can simply work out the domain and range from the original function and then swap the domain and range also. Alright, third example is we're going to have a look now at sketching a slightly more complicated log graph where we have to find the x and y axes intercepts. And I'm worried that the one I've selected is a little bit too straightforward, so I'm going to quickly choose a different graph. Let's actually sketch. We won't use y, we'll use the function notation. Let's sketch f of x equals log 2 x minus 4, and we need to state the domain and range. And find the x and y axis intercepts. And because I'm quickly making this up on the spot, I'm going to change that to a plus, so I actually get an x and a y axis intercept. So we're sketching f of x equal to log to the base 2 of x plus 4, and we're going to state the domain and range and find the x and y axis intercepts. Alright, my process for doing this is I start with a quick sketch and look at the transformations to consider where my graph's going to go. So my original log graph has an asymptote at x equals 0 and goes like this with an intercept at 1, 0. And then from my transformations here, I've got a plus 4 inside the brackets, so that's going to move my graph left 4 places. So I know that my new graph is going to be back over here somewhere. If I've moved 4 places to the left, that's now x equals 4. And my intercept is going to be at minus 3, 0, because I've moved back 4 places. Alright, before I draw my good graph, I can now see that I'm going to have a y-axis intercept and an x-axis intercept. So let's find the values of each of those points before I draw my good graph. So my y-intercept is when x equals 0. So I'm going to get my y value is when I substitute in x equals 0, which gives me log 2 of 4. And remember our language of logs, this is saying 2 to the power of what equals 4, and the answer to that is 2. My x-intercept is when y equals 0. So write my equation, log to the base 2 of x plus 4. Now here I'm going to put each value to the power of 2, which cancels out the log, which gives me 1 equals x plus 4, and then subtract 4 from both sides, x equals negative 3. So that quick sketch graph before matches with what we've just found. Now all we need to do is draw my good copy, or my final detailed graph with all of the intercepts and asymptotes drawn on there. So I'm going to call this value here 2. I'm going to call this value here minus 3. So that's negative 3, 0, 0, 2. And then I have an asymptote at x equals negative 4. So keep saying, always add the equation to the asymptote. And as you can see before, I had this wrong in my quick rough graph. By doing this a second time, it gives me that chance to fix up my errors. And then join my points, get the shape right. I have my log graph of f of x equals log to the base 2 x plus 4. And finally, I can say, well, the domain, that's the values that x can be. So that's everything that is bigger than 4 up to infinity. My range is everything that y can be, which is r, or negative infinity to infinity. And that's the end of my 3 examples for graphing logarithmic functions.